In this video, we will work on one type of model that has been foundational for accounting research and that spills over into some finance research as well, and that is models that are used to predict earnings. Some of the things that are in here we've already seen, so all of these packages and these functions that we've created. I've got a new data set here. It's earnings forecasting data that's a little bit different than what we've had so far, but overall very similar. So we can open up that data set and look at it. It's bigger, so we've got more years here in the data. We have the GV key again and the industrial classification code fiscal year, but the items that we have are slightly different. So let me talk through them quickly. This column, REVT, is total revenues. We've seen that before. This one is operating expenses, then other expenses. So revenue minus operating expenses minus other expenses is net income. CFO is cash flow from operations. CHE is cash and cash equivalents. This one is working capital. This one is property, plant, and equipment. Capital expenditures, total assets, total liabilities, shareholder equity, and the market value of equity. So these are the things that we will be working with. We won't use all of them in the video. They will be available for the homework. So I'm going to create variables that I can use for the models. This one here is going to be the net income that we will predict. You can see that most of the variables are divided by market value of equity. This is just following prior research. We divide by something to make measures that we're going to use comparable across companies. There are some debates about whether that should be market value of equity or common shares or total assets, or if we should not be dividing by anything at all. So I'm going to show you one of the most common ones, but there's no reason that we have to choose this as the thing to divide by, or even if we should do so, but this is what's most common. So we have these variables. This is the one we're going to predict. All of these other ones just come from research that says these are some of the best variables for predicting earnings, and we'll just set those up. In terms of functions that we're using here, you've seen all of these before, so there's nothing new with that. We're going to remove missing values and then remove outliers. One thing to notice here is I have this variable. This is an indicator variable that is equal to 1 if earnings are negative in year T and 0 if they're not negative. And we've seen this before. This is a true or false. Net income is less than 0. This will be true. If it is negative, it'll be false if it is positive, and as numeric turns true into ones and false into zeros. Well, this is a 1-0 variable, so we don't have any extreme outliers. So when we get down here to do outliers, that variable is not in here. All of the other ones are divided by market value of equity and are continuous variables, so we're going to apply this outlier function to get rid of the outliers. I just keep the variables that I want here. You could look at the data. It looks similar to things we've looked at before. And I'm going to split the data into years before 2005 and years after that. I'm going to use the years before 2005 as the training data. The model setup that we're going to use here is similar to what you've already seen. We're just predicting future earnings. This first model only uses earnings from T to predict earnings T plus 1. I'm calling this my benchmark, and that is because these other papers have found that the best predictor of future earnings is current earnings, and it's hard to beat that with models that include other variables. In the slides, we'll talk about some of these other models. These are the other models that have been proposed, so I'm estimating these other models here. That gives us 4 linear model estimations, and notice I'm saving each of those models as a model object that we will use when we evaluate how the models worked. Then we have this k nearest neighbor regression. This is new, but the setup is very similar to what you've seen before. So we're using the caret package. We're using this train function. I'm going to set up this control for the training, and I'm going to leave that in there for everything else that we're going to use. The main difference here is this KNN. So what k nearest neighbors does is it searches through to find K observations that are most similar based on these X variables. So it's related to the clustering we talked about before, and by K it's searching through how many nearest neighbors to use to predict what earnings will be in the next year. So it's fairly straightforward. It's a little bit computationally intensive because it has to search through every single possible match. So that's the K nearest neighbors regression. We can run this. I'm going to set seed for all of the different machine learning models we have. Let me walk through a couple of the variations of this KNN model. Here's the default method. Then with any training function in Caret, we can pre-process the data, which is similar to when we standardized for the k-means clustering. So this pre-process function says center all of the variables and scale them. So standardize them is the scaling part, centering them is moving them all to be mean 0. What this does is make sure that when you're measuring how similar a company is to another company, they're all on the same scale. So it seems to help, but we can see if that helps by using that as an option. Notice we didn't have it here. So the difference between this second estimation and the third one is I put in other variables. What one of the papers says is this model, just using earnings from t minus 1, and t minus 2 is the best you can do with this k nearest neighbors modeling, and by adding more it doesn't help much, so that's to test this. And then finally, this tuning grid here, we're going to force it to try a bunch of different numbers of nearest neighbors, so from 5 up to 100. Otherwise, it might stop before it gets to that point. So this is forcing it to do a little bit more. So these are our 4 k nearest neighbors regressions. I will run that in just a minute, but then we will also do the XG boost, and I'm going to use something like what we did before. I'm just going to force it to use more trees, so I'm going to do 100 and 200 here, and for max depth, I'm going to try a couple of different ones, 10 and 50. Of course, we could expand this to be lots of numbers and to force it to try a lot of things. And if we were going to try and implement this as a way to predict for some decision making, we would probably try lots of things before we settled on a parameter that we were happy with. So other than that, same thing here. That's going to be our XG boost, and that also follows one of the papers that we talk about in the slides, is this extreme gradient boosting and how that can help. Then we'll try 2 neural network models. I need to point out a couple of things. So the first one, we're going to use some of the defaults. I'm not going to do this tuning grid. So that was just there to help you recognize that we could do it, and you'll see it in the next one. And we need to add one more thing here. This lin out equals true. What that does is allow the predictions, so we're trying to predict for earnings next period. It allows those predictions to be outside of the interval 0 to 1. The default is to use prediction intervals that only fall in this range. Of course, in the earlier one, we had predictions of growth that would go outside of that range, but it turns out not to matter so much because those growth models are not very good. So here it does matter. So we need to put in this linear out equals true. So that'll be our first one. Then we'll force it to do some more on the neural network model by expanding the grid here, and I'm going to add some complexity, so moving it from 5 up to 20. This is how many layers there are in the neural network model, so trying to make it go a little further, and then we'll run this one. After that, we're going to look at how they all perform, and we'll come back to that in just a minute. So I will run this and let it run for a minute, and then we'll go over how they perform. Now to look at the results, there are a few output things we can look at to understand a little bit the models. So this one, if we just output the object, it'll tell us some of the summaries of how it did that KNN regression. So up here just tells some of the details of it, but this is the main part. It says if we use 5 nearest neighbors, meaning the 5 most similar companies to predict a company's next year's earnings, we get a 17% R squared. Notice if we use 7, we get an 18% R squared. If we use 9, we get a 20% R squared. Well, why would it be that the more neighbors we use, the higher the R squared is? Well, that's because if we use a single neighbor or a small number of neighbors, they may be not very similar to the company that we're trying to predict for. So sometimes getting more neighbors can improve prediction. There's a trade-off there. If it gets too high, then it can get worse. So we can look at the other one. So if we look at the one where we pre-process, notice the R-squared value. So here we went from 17 to 20. This one went from 17 to just under 20, so our R-squared decreased a little bit as we centered and scaled things, and then we add more variables to it, and it increased it just a little bit, so 21 to 24%, and this one we centered and scaled and added a lot more, and we went across this grid of 5 to 100. Notice it settles on 50, going from 21, 25, up to 100, and 50 and 100, it goes up to 28%, but it starts to increase more slowly when we get up here. So it stops at a point where it's not increasing much anymore. So it says here 50 maybe is about the best. Of course, we could mess around with that some more, but that is the same as the pattern we saw before, that increasing the number of nearest neighbors increases the R-squared sum. Presumably, if we kept increasing it, it would get worse. Then the XGBoost, we've looked at this before, but let's just look at a couple of outputs here. Again, the variable importance on this XGBoost model. Lagged earnings is the most important. That's the same thing that other research has shown, is it's hard to beat lagged earnings as a predictor. And we can get a little more information just by outputting from the object itself. So we can see these are some of the defaults that we put in. It says here the final values used for the model were 200 rounds with the max depth of 10. So we go up here, what we did is input. So here we have the number of rounds, the number of trees of 200 is the maximum. It ended with this of 200, so that's the best it could do. So we could go and adjust this even more, maybe go to more than 200, but gives us a little information there. So then let's look at the neural net ones. We could do the same thing. Look at the variable importance. Notice here it's not earnings anymore. That's the third most important. We have these other variables that are important. So here we see that the size that it used was 5, so it's going from the default across different levels of complexity for these neural network models. So here I'm going to start with 5 and make it more complex and see if it improves the model at all. So we can look at what happens with the second model. Notice now it has earnings as the most important, so that's flipped things around a little. And it tries over these different sizes, so the smallest is 5, then it does 10. Notice it goes up just a little bit, but not a lot, the R-squared. And 20, it gets worse, so apparently somewhere in here it starts to get worse because it's getting too complicated. And so the one that it used and stuck with was 10. So perhaps we improved just a little bit, but it's not much difference between 5 and 10. So then what I'm going to do is look at the R-squared values in sample and out of sample. This should look familiar. This is the R-squared calculation, and I didn't want to do that over and over and over again, so I created a function for that, and the inputs for the function are the model that was used. So you can see down here I'm inputting each of these models, the data set that was used, and the variable that we're trying to predict. And once I have that function, now I can just create an R-squared value for each of the models we used. So I'm going to create a data frame, and it's been a while, but we've done this. And each part of the data frame, we're going to create this column, and I'm going to use the model, the training data set, and the training next year's earnings. So I can run this, and that's going to give me all of these different models that we've tried to use. So once we run this and get the function, we can set up this data frame and output the data frame that I created. It takes a little bit because a couple of these take some time to fit, and in particular these K&N ones take some time to do the predictions. So what comes out of this is all of these columns, and in the first row are the R-squared values. So let's talk about what we get from that. So the benchmark here, this is the one that is hard to beat in real prediction, and it gives us a 19% R-squared in the in-sample data. Our other linear models, notice they increase the R-squared as you go from simple to more complex. So it would appear that at least in-sample we're getting a little bit better of a model as we move to the more complex models. And then looking at the K&N regression, Notice all of those are higher than the benchmark and higher than all of the linear models. This is similar to what the paper that we talk about in the slides is finding. And the XGBoost model is also better than all of these linear models. So again, that's similar to what one of those papers found. And our neural network models, they're pretty similar too. So we're all in the 30% R squared range. Perhaps we could get even higher, but there's sort of this range here. And we could think about each aspect of why one model might be different from others, but here I just want to focus on, at least in the training data, some of these other models seem to do better. So we can do the same thing with the testing data. Notice I just replaced this testing data set and the testing thing that I'm going to predict. And we're going to run that for each of those as well. It'll take a minute or two. So with our testing data, we happen to luck out. Our benchmark model actually is a little bit better when we move to the testing data set, as are some of our other models. But notice the difference has sort of gone down. So these linear ones are maybe not quite as good. This one actually did slightly better. We don't have any, at least, these two are not quite so high. We still have one here that's near 40. And these other models are sort of in the same range as well. So perhaps going in and out of sample, these models are fairly similar. And there seem to be some that actually do outperform the benchmark model in what we might think is a sort of consistent way. So perhaps that paper that says that the KNN models might outperform the benchmark model, that seems to be likely. The other ones, this XGB, at least that current version doesn't seem to be too much better than the benchmark model. And these neural network ones do seem to be better. If we want to get it in a visual comparison, rbind combines rows of data frames. So we can combine this and we can look at both of them. So the benchmark, it actually got better on the training data set. This linear one didn't get much better. These ones got a little bit better. KNN1 got worse, so now it's closer to the benchmark. KNN2 got worse. KNN3 got worse. KNN4 happened to get better. So we may not be super confident that any particular one of these would actually do better, which would get to some other methods that we might consider. This one got worse, these ones got better. So overall, what can we conclude? Maybe some of these models could do better than the benchmark model, but the evidence in my mind is not super strong and compelling. It's not like we have this benchmark model that's hovering around 20, and these ones are all consistently 40 or above. It's not that sort of improvement. So maybe there's some evidence that we can improve. We have some other things we could do by adding other X variables, and some of those are available in the data set that you have. We're going to look at a couple of other things that some people have tried to look at that help explain some of what's going on, and then also are used to try and improve models. So these will give us other tools that we can use in the class and in R, and might give us ways to start thinking about how to improve models, although we won't go into trying to really use them to make a better earnings model, but it'll get us some tools to work with. So these tools here, we're going to add the tidyr package, the broom package, and the purr package. And tidyr is the one that probably is most useful here. Broom is next, and then maybe purr is after that. So one question we might have is, what if the correlations in the model are changing over time? So one reason that we see that some of the models work better when we move to the testing data set is because things have just changed in the data. So I'm going to combine our testing and training data and look at both of them, and we're going to look at over time how some of those coefficients have changed. So first, let me introduce some of these tidy and broom functions to help you understand sort of how this works. So when we run a regression model on all of the data, I'm just going to keep it to these 3 X variables. So I run this. This is something we've seen before. If I do a summary of it, this is what it looks like. Well, in terms of working with that data, this is messy. So that's what tidy is supposed to be doing, is it creates a data frame in a tidy format that allows it to be useful. So if I run this instead of summary, I run tidy. Now it's put it into a data frame that I can use, and I could save it and work with it, and we're going to use that. It has other functions here too. This glance function, that just looks at a high-level summary of this part of this model. So it's like the summary function, but it only outputs the model fit variables. So here we get R squared, adjusted R squared. These are some other things that we can look at that talk about model fit, other measures of model fit. In concept, they're sort of similar to the R-squared, but they have different properties. Then this augment one, what it does is take the model and then fit it to the data. So it's just putting in the model the fitted value, so the thing that would be predicted based on that model, and other outputs from the model. So I'm going to augment this data set. I'm going to save it as a try object. I look over here, open it. We've got the variables that were used, and then this fitted value is the variable that would be predicted based on the model here. So these are the values. The coefficients are hidden here. They're not in this, but they're used to create this fitted value. And then the residual is what is not explained by the model and some other stuff too. So different ways to be able to capture output from the models. We're going to use this tidy one to then run a model by year. So I'm grouping by year. Notice I'm going to run this model, and then tidy is going to move it into a data frame like we already looked at. And do tells it when we do this grouping by year, we're going to do this regression and make it in a tidy format. So look at the output. So what it does is for each group, and by group here it was years, it provides the estimates, the standard errors, statistics, and p-values. So in other words, it takes the tidy format of the model, outputs it here by group. So we've got 4 for this year, 4 for the next year, and it'll keep doing that for every year in the data set. Well, perhaps we want to see how it works over time, so we could pull out just a specific one of these terms and look at those over time. Another way to do it is to move these and reshape the data in a way that we can use it for graphing. So we will do that when we look at the next setup here, which is basically the same thing, but we're going to rework data. Another way is to graph, but group by the thing that we're trying to look at separately. So if we look back here at the output, we have earnings, we have negative earnings, and the interaction. The coefficients on all of those are in the estimate column. So we could separately look at this earnings one for all years and separately look at this negative earnings for all years. Well, when we graph, how we can do that is make the color a function of the term or the line type a function of term, and the rest is like what we've already seen in ggplot. So I'm going to plot that. What that's going to do is give me the coefficient estimate for the y values each year, but it will group it by this term and create separate lines for each of those terms, which are the different variables. So we can look here and see we've got the coefficient on earnings was near 0 back here, then it went negative around 2000 and has basically stayed there since then. So the coefficient on earnings is near 0 and negative. The coefficient on negative earnings, it's a 0, 1, so going from having positive earnings to going to having negative earnings. On average, the next year, it's still slightly negative. And then this part is, I think, part of what's driving some of the results that we see moving from the testing and the training data set, because here is where our split was. So back here, we had the training data. Over here, we have the testing data. And what has happened here on this coefficient on the interaction between earnings and negative earnings is that has gone up over time. So what that means is if you had negative earnings in year T, that earnings in year T is associated with future earnings, positively associated with future earnings. Meaning if you had more negative earnings, then in year T, you had more negative earnings in year T plus 1. If you were closer to 0 in year T, you were closer to 0 in year T plus 1. On the other hand, the earnings side, so this would be positive earnings. As you go over time, positive earnings is more negatively correlated with future earnings. So controlling for this negative earnings side, if you had more positive earnings in year T, you have slightly less positive earnings in year T plus 1. The main thing I wanted you to learn from that is that the coefficients, the correlations that are occurring in the data are changing over time. And that can cause some challenges to when we try and model this stuff. Another one that people have raised is maybe different industries have different properties to their earnings and how earnings are correlated with other things. So we could run this by industry. So I'm going to create an industry variable for the training and the testing data set. And I'm going to run this model on the training data set. And I'm going to do two things. One is to look at the tidy. So remember, that does the coefficients, the model output that we've already seen. Glance does only the summary information. So we could look at both of these here. And let's look and see what it looks like. So out has 36 observations, out 2 has 9. So let's look at the 2. So the R squared, this is industry 1 through industry 9. So notice the R squared is different for each of those industries. Then on the one where we use tidy, it looks the same as we had before, but instead the groups are by industry rather than by year. And so then we could look and see that these are different across industries. So then maybe we want to use that to apply and create some predictions and look how that would work on the testing data. So we're going to do a couple more things. This one is adding the package reshape2. And what that does is do some transposing of the data. So I'm going to use this recast, take the out data. So remember, this is this data. What I'm going to try and do is take just this column, the estimate column, and use term and create those as the columns for each group. So how you do that is you have this formula here that says we have industries, that's the thing that is going to be in the rows, and term is the thing that is going to become the columns. And the measure we're going to use, this measure.variable, is the estimate column, and we need to tell it what those ID variables are, which are going to be this industry and this term. So we can look at this and notice what it did is twist it around. And so we have the industry column that gives us each row group, and it has flipped the coefficients to go across the rows. So for industry 1, these are the estimates that came out of our regression. And it changed the ordering here, so we have to be a little bit careful in the next step. So it has earnings here, then it has the interaction term, then it has negative earnings here. So I'm going to rename these columns to make them easier to work with in the next step. And you do that by saying we have these names of this data set and providing all the names in this list that is given by C, that creates the list. So when we go back and look here, I've renamed all of these for use in the next step. All right, we need to think about how do we create an R squared that provides a different prediction for each industry, which is a little bit complicated. So let me walk through how we do this here. So we have this data set that we just created, out3, that gives a coefficient for each of the industries. So what I'm going to do then is join on our training data these coefficients. So when I go look at the training data, and I'm now calling it train 2, we have the data we had before, and then at the end we have these coefficients that apply to each company then. So this company that is in this industry, or 5, which then is this industry over here, I can use these coefficients that I calculated to multiply by these things that I used over here. So these are the X variables. So here, this earnings, negative earnings, and then the multiplication of those, I can apply those to these coefficients. So how I'm going to do that then is just like we have done with the predict function, but here we do the algebra. So we take the intercept, add the slope times the X variable for this one, add that to the slope times the X variable for this one, plus the slope times the X variable for this one, and this X variable is those two multiplied together. So this gives me the fitted value that I've used to explain next year's earnings. I can then, in the same way that we've done before, I can calculate the R squared from this function that we already had. Okay, so I can run this whole thing, and it outputs, this gives me a 22% R squared. Notice this is a simpler model than we used. It's sort of like the benchmark model, but with these two other columns in it, and it improves the R squared on the training data just a little bit. So perhaps that's better, right? If we go back to look at what it was before, train R squared. So the benchmark before had a 19% R squared. This one is a 21.9%. That's sort of like our other linear models. So it may or may not be the case that estimating it by industry improves things, but estimating it by industry at least improves so that we're sort of in the range of these other linear models. We can do the same thing on the testing data set. Notice I just changed to using the testing data, still merged on the same coefficients. Run this, and we get 27% R squared. So let's go back and look at how these other ones did. So the benchmark model went from 19 to 25, linear 21 to 25, linear 2, 21 to 28, 25 to 30. So in other words, estimating by industry gets us kind of in that same ballpark of using a more complicated model. So we could use a model fitted on the industry. Perhaps that works a little bit better than the benchmark model, but it gives us something to work with. And it introduces a lot of other more complicated coding stuff that we might use to work with the data.